Hello everyone and welcome to a new discussion which is part 2 of hydrological cycle. It is something like films, part 1, part 2. So, it is a film on groundwater engineering. So, one should take in that spirit and try to learn as many as details and intricacies of groundwater, and of course, before that we have to learn overall about the water hydrologic cycle and other things. So, if we want to do the quantitative determination or estimation of evaporation from the surfaces which we have just discussed, like sea, oceans or lakes or water bodies or rivers, then it is estimation is not very straightforward. It is a complex problem, and since it is because it is influenced by many factors, and these factors are dynamic, constantly changing factors are there. So, different seasons the evaporation changes also. So, like when we are having heavy rain or intense irrigation intense irrigation is very common in Indo-Gangetic plain because plenty of water is available in groundwater conditions, and also through very dense canal network. Perhaps the densest in the world in the Indo-Gangetic plain. And so, this saturation levels of solid moisture reaches in the surface or near surface in the soil layers. So, the soil is most of the time is having moisture in such conditions, that is heavy rains and irrigated land, and therefore, it is a good source of supply of evaporation. So, there it can be estimated, but for different surfaces the estimations would have to be different. So, evaporation from soil surface forms one of the major components of groundwater losses in discharge and waterlogged areas. So, if we want to recharge the groundwater regime, then these losses have to be reduced, and then probably we can achieve better groundwater recharge and can store more water into the subsurface, but it is not very easy to reduce these losses. Anyway, so it varies with the depth of water table and the texture of soil. Why varied with the depth of water table? Because in shallow groundwater conditions, like again I am giving example of alluvial plains, Indo-Gangetic plain or other areas where the groundwater conditions are shallow, more evaporation will occur. And not only evaporation, but more evapotranspiration will occur, because in such conditions the soil will have moisture, and if the soil is there, moisture is there, then there will be growth of vegetation, whether it is a agricultural land or natural growth of vegetation in form of forest and other bushes and other grasses can grow also. And of course, another controlling factor of this evaporation is the texture of soil. Different soils will behave differently from evaporation points of view. So, evaporation from a greater depth is only possible in clay soils with high capillary rise. Why it is so? Because clay particles are very fine particles. If we see the the sand particles or these sediments, then we start from boulders to clay particles. So, clay particles falls at the lowest level, that means they are having the very fine sediment. They are considered as the finest sediments, natural sediments so, if the soils are formed mainly clay particles, then whenever there is these gets dry, then a lot of spaces are created, and you might have seen the mud cracks and other things also. So, in these the capillary rise is very common, and therefore, evaporation losses from these types of soils are very high. And one view graph is shown here, that on the x axis we are having depth to water table which is shown in inches, and this is the percentage of pan evaporation. Evaporation is estimated when you fill in a pan whose surface area is known. So, you know that how much depth of water or percentage of water is being lost. So, if you go towards more deeper water table, then the losses decreases. But whereas of course, the shallow groundwater conditions will always support the high evaporation. Similarly, we can also see little more in detail that relation between potential evapotranspiration and the rainfall and the soil moisture during periods of alternate dry and wet spells. So, if this scenario happens, dry and spells, then there will be more there might be more evapotranspirations. So, we are having a say starting from here, these are on the x axis we are having the months, and on y axis we are having values of this evapotranspiration losses. So, what we see that here initially we are having deficiency and here we are having withdrawal. So, more withdrawal would be there if the soil moisture is less, and the soil recharge, if a wet spell comes, then soil recharge is there, then there is a surplus of water, and then there may be again a dry period. So, that this cycle keep going on. So, EP is the potential evapotranspiration which is shown here, and also EP is this part, and then EA is the actual evapotranspiration which we are seeing in this section, and of course, the precipitation P is there. So, when precipitation occurs, soil recharge occurs, water may be surplus in the soils. Now, evapotranspiration, and we have been indicating, discussing this, that this is a total loss of form of vapors which are formed either through land surface and from the plants. So, it is a sum of evaporation from the land surface plus transpiration from plants, because it is very difficult to isolate. If it is a simple open water body, then we can very well measure the evaporation losses. But if there is a mixed kind, then land is there and then vegetation is there, open areas are there. So, then it becomes very difficult to isolate whether the losses are because of evaporation or transpiration. So, we give a common name, that is evapotranspiration, that is the sum of evaporation from land surface plus transpiration from plants. Now, in the previous figure I have used this term potential evapotranspiration. So, it is time to define is that this is the amount of water that would be evaporated and transpired by a specific crop, an ecosystem, if there were sufficient water available. Now, these things are nowadays in agriculture, I would use term technology. So, in agricultural technology, these are the things which are estimated or being tried to estimate as accurately as possible and as in advance, but to imply whether satellite technology or drone technology or GIS and other things, to estimate these things. So, that the whatever the crop is there, a specific crop, when it will require more water or when it will require less water, those things can be estimated, and accordingly the irrigation can be planned. So, it is a though we are discussing only say water cycle, hydrological cycle, but a hydrological cycle is a part of our system. So, our agriculture also depends on all these things, and especially evapotranspiration. So, the availability of water or timely availability of water is good for the growth of agriculture or a crop. So, a specific crop will require water at a specific time, more water every time. So, evapotranspiration, as I have already said, is a sum of transpiration and evaporation. So, here if it is only plants are there, dense forest is there, then we can say that most of the losses which are occurring or most of the vapors which are being generated in the atmosphere are because of trees. But if it is an open surface, a water body or grassland or bushes are there, then we say this is evaporation. But when it reaches into the atmosphere mixing, then it is overall it is called evapotranspiration. Some water may also go in form of groundwater recharge. So, there is always difference between actual evaporation and potential evaporation. So, here the curves are shown on x axis you are having months in both the figures, and here you are having depth of basically precipitation. So, what is average monthly precipitation and then potential and actual evaporation for some places are shown, but these are unfortunately not from India. Anyway, these experiments have done, but they are just to understand the this phenomena evapotranspiration losses, we need to go through this one. So, we are having these solid squares are showing the precipitation, then these circles kind of thing, empty circles are showing potential evaporation, and the third one is actual. So, what we hear, the potential evaporation has been overestimated, whereas actual has been not as that one. But there is a direct link, as in the previous slide which we have been discussing, that there is a direct link with the dry and wet periods or rainfall. So, as precipitation has increased, the actual evaporation or evapotranspiration has also increased. But however, the potential was more estimated here. In another place, that is the Peterborough, there it is again rainfall is almost constant relative to the first diagram of Saskatoon. And what we see here, that of course, when there is a less rain in that particular geologic conditions, surface conditions, again the potential evapotranspiration was estimated more, but actual was also has occurred more, whereas the rain has been there. So, the point which I was also mentioning earlier, and will keep repeating that point, that everything depends on local areas, local geology, local topography, local vegetation cover, because if one model cannot be implemented on for the other or cannot be replicated for other model. As two examples which we are seeing, of course, they are from foreign countries, but nonetheless they are showing that results are different. So, that is the one can say the real challenge in groundwater engineering also, or in hydrological sciences as well. So, a hydrological cycle which overall which we are discussing is part of precipitation, as we know, is what intercepted by plants and then directly returned to the atmosphere through the evaporation or transpiration, and part of the water reaching the ground and making up the soil moisture, which is later evaporated through the leaves of transpiration. So, directly there is loss of water in form of evaporation, indirectly after they are falling or making soil rich with water, and then again through plants, trees, it is water which is going back. So, evaporation is here, and then transpiration is also shown, and then it is the losses there are there. So, transpiration rates may be extremely low in xerophytic plants. Now, nowadays a lot of discussion in hydrological domain is happening about these xerophytic plants. These are adaptable to survive in an environment with little liquid water. So, in the upper part of this figure here, what we see that these are the xerophytic plants. They do not require much water, and the water which they get, they get the water many times from atmosphere directly, and these are common in deserts. However, they vary in their hypothic this hydrophyte plants. So, there are xerophytes plants or xerophytic plants, and there is a hydrophytic plants are there which live in water. So, the lower part like lotus in India and many such plants in water bodies in India can be found. So, they are hydrophytes plants, which are again are becoming very important from managing the better groundwater or managing better surface water quality, because these plants are capable of absorbing lot of pollutants from the surface water, because they live only on the water, mostly on the water, and in order to grow they consume lot of nutrients. For some time we may feel that these are harmful for the humans, but plants can grow or survive or flourish. Let me give you one example. Many of you might have been to Dal Lake in Kashmir in Srinagar, and Srinagar water earlier in past time, that lake water was not very clean, and what is happening that a lot of these float farms were there, and they were growing vegetation. And if you see a say like cucumber, if you see a cucumber in normal size you may find in plain areas or other parts of the country maybe 6 inch or 8 inch. But there, because of high nutrients were available in the water, and these through their floating plants, that nutrition were fed to the cucumber creepers, and they were able to grow creeper or these cucumbers of more than 1 feet. Likewise, many gourd and many other bitter gourd and many other vegetations were growing very with the big sizes, and of course, the taste was also there, because they the all nutrients which were required to grow large these vegetations were available through water body. But in from hydrologic cycle point of view or from human life point of view also, both types of plants are very important. So, xerophytic plants which require almost zero water, and this hydrophytic plant, they survive only in water. So, why the xerophytic plants are important? Because if a lot of plantation is there of xerophytic plants in desert areas, then we can decrease the this encroachment of deserts in the fertile land. And these things have been happening in some parts of India, where in earlier times the deserts was encroaching agricultural land. Now, but change in the rain pattern and also these kind of efforts, xerophytic plants plantation and other things, this encroachment of deserts have been reduced in some parts in India significantly. And another important thing is that many of these xerophytic plants are having medicinal value. So, this hydrophytic plant. So, both types of plants, or I would say all types of plants, are useful in some way to another to human, and they are all part of our hydrologic cycle. So, hydrological cycle of the earth is sum of total of all processes. Earlier we mentioned complex and dynamic process. So, all these processes in which water moves from land to ocean and surface to the atmosphere and back in form of precipitation, and this precipitation can be in form of liquid or as in solid or in form of like crystalline like snow. So, the hydrological cycle is intimately or interconnected with the changes in atmosphere, temperature and radiation balance. And in previous lecture I have little touched about global climate change which are happening, and because if we say that the temperature are changing, so that our this normal hydrological cycle will definitely disturb, and more evaporation might occur. But there is some other time we will discuss on how this global climate change is affecting our overall groundwater scenario, and what are the impacts which are going to cause or already causing in groundwater. But if more temperature there, then more radiation might be there. So, this will increase the evaporation, more losses of water from the surface to the atmosphere, and that might create problems for at least for the agriculture, for forest and for overall for humans on the surface of the earth. So, it dependent on various factors, few factors I have already mentioned, the temperature and other things, and is equally affected by oceans and land surfaces, because the downfall of global climate change or temperature rise, global temperature rise is that the sea level rise, and that means more surface area is becoming available, sea surface area for evaporation. So, that is another warning or to us also. So, because of high rise temperature or high temperature, because of global warming, the climate system in recent decades is unequivocal, and it is now evident from observations of increases in global average air and ocean temperatures. So, the not only the temperature on the land, that means land surface temperature is increasing, but subsequently and I would say simultaneously ocean temperatures, ocean water temperature, sea water temperature is also changing, and this all will go for more higher evaporation losses. But earlier I said that the not even a single drop of water can go out of earth system, because it will go in atmosphere, it has to come back. So, in long term we have to see how these impacts will occur, whether there will be more rain or not, and if more rain, then what would happen to the temperature. These are the things which one has to understand in future, and this is what it is now people are focusing. But we will keep our focus only for current discussion on hydrological cycle. And then of course, temperature rise will increase the snow melt and glacier melt and so on and so forth. So, there will be, in case of land surface, vegetation plays an important role in the maintenance of hydrologic budget, which we know, and because two processes or many processes are controlled by vegetation. Precipitation directly is not coming, it is intercepted by vegetation. There will be a transpiration, there will be evapotranspiration, evaporation, then through fall, and sometime through fall is good, and then you are having untake and uptake and other water is, and then finally it goes to as surface runoff or drainage. So, presence of vegetation increases the capacity of land surface to retain moisture. So, if there are more evaporation, there will be more rain, then there will be more vegetation, that will allow the soil to retain the moisture, whether that because of high temperature, again that can go back to the atmosphere. Anyway, it is a very complex situation. So, precipitation is less, is then intercepted by plants and directly evaporated and then captured by the canopy. And also the plants themselves transpire and aid in creation of major amount of water vapor through evapotranspiration. I said in the earlier discussion that in western UP the agricultural lands are always green, and they are pumping the vapor, you can say, because of high temperature they are pumping the vapor into atmosphere, and that is what is causing high humidity in this area. So, surface runoff in case of bare ground is much greater than vegetated lands. So, that means we need more vegetation to intercept the precipitation, to hold the water or delay the surface runoff, and that will allow the soil to become saturated with water. And then if soil becomes saturated with water, that will allow water to go downward and through this infiltration, percolation, and finally to the groundwater recharge. So, as plants we know that dominate the processes of energy, water vapor and carbon exchange, that is another very important component of and not directly related with hydrological cycle, but overall as survival of the on the earth, that carbon exchange is also plays very important, and their presence is critical to the functioning of hydrological cycle. So, overall we have discussed few major points are here, and summary kind of thing that the concept of hydrological cycle is simple. It is quite simple. Major things are there, that you are having precipitation, you are having then collection, you are having evaporation and then condensation, and this cycle goes on. And but it is important on the for the life on the earth. So, our life depends on this whole cycle, and it plays an overarching role in cycling of solar energy, sediments and chemical elements vital for life. See, if I just discuss little bit more on sediments, whenever there is a like an Indian system, whenever there is a rain, lot of sand, lot of sediments will come in the streams, and and they are required for many construction works. So, in some way it is advantageous, but how these sediments are coming, that means through the weathering and erosion of rocks which are on high reaches or high hilly regions or like in Himalaya. So, these sediment supply is also there. If we assume that this kind of rain does not occur, then we will not have much sediment supply in the rivers. So, this is a cycle, things are interrelated, complex, in a complex manner they are interrelated, and this keep happening and they keep providing some better results, sometime flooding and some hazards to the humans, but nonetheless it is a cycle, water cycle. The importance of functioning of geological and biological earth is profound, exceeding water itself. That is for both geological example I have just given and then biological sustainability. This is all, the water cycle has to keep moving, and then the life will be, if by some means, because of some dramatic changes, if there is a big interception because of some major changes, then the entire life on the earth, not only the human life but vegetation life will get affected. But it is a, whatever the changes which are occurring, if we talk about global climate change or land surface temperature change or sea surface, these are slow things, and nature also adapt to these changes, plus humans also. So, water on surface and in the streams and lakes infiltrates the ground to become groundwater, where our ultimate focus is going to be in this course. How to know that how the water is going to the groundwater regime and how to improve that situation. That is what our focus is. So, groundwater, as we know, slowly moves through the rock and surfacial materials. Surfacial materials might be soils, might be weathered rocks, might be rocks with fractures, joints and gaps or cracks or whatever is there. All this will allow water to go maybe slowly towards the groundwater regime and may recharge our aquifers. May not be directly, may not be immediately, but maybe little later. So, some groundwater returns to other streams in form of springs, and many examples I have given of Indian river systems. Again I will narrate, like Narmada. Narmada is not fed by snow or ice, but it is perennial river. So, it is, that means it is fed by the groundwater through springs, and lakes, and some other goes directly back to the oceans. Let me give you an example of a lake, and many of such lakes are having springs in the bottom or in the base, like this Nainital lake. So, there are many springs located at the bottom of the lake. They are feeding this lake, they are bringing water, and of course, in monsoon season the springs are bringing more flow, and therefore, you are having more water. In summer season you are having, but springs, because of springs it is there, but these springs might be fed by snow and glaciers. But a river example I have given about Narmada, there is no snow and ice, but still. So, we are reaching almost end of this hydrological cycle discussion, that water storage is also part of hydrological cycle, wherever it is stored, either in oceans, seas, lakes, streams or in groundwater. And the largest by the oceans, of course, we know, as is shown here in the blue part, that 97% of water is stored here. Earlier in the beginning of this course, I have also showed the distribution of water, but now we are only discussing where it is stored. So, the large part, 97% of water is stored in oceans, and then though it is directly not usable for human consumption or irrigation, because it is salty, it is having various salts in it. But there are techniques people are developing which are creating from salt water or sea water to fresh water, but these are expensive solutions anyway. Then remaining 3% is fresh water, only 3%. Out of whatever the hydrological cycle or whatever the water available in earth system, only 3% is fresh water, and 2/3 of the fresh water is stored in ice and 1/3 is stored in the ground. So, very tiny amount, as you can see, 0.9% of total water available on earth system, in earth system is as groundwater. But it is important, very important for sustainability of life in many parts of the world, especially in India, as we have seen also in earlier discussions, that large human population and agriculture depends on groundwater. So, we have to augment by our understanding, by science, by technology, by engineering, if we can augment and can create instead of 0.9%, 2% groundwater, then lot of groundwater problems will be solved, at least for this country. So, lastly, the remaining fresh water, about 0.03% of total, is stored in lakes, streams, vegetation and atmosphere. So, the lake water and stream water is also being used to grow crops, to supply water for drinking water in cities or in even in villages. So, that 0.03 is also because it is fresh water, it is also used, but overall groundwater is only 0.9% of total water available in earth system. So, with this thank you very much, and we end this discussion here. Bye.